Okay, so welcome to another video. So last video we've derived formulas and we've discussed theories that we need to observe when we are dealing with Carnot cycle. So right now, let's try to answer or to apply those principles and theories from before in a sample problem. Okay? So in solving gas cycles, the number one tip that I can advise to you is the first thing that you need to do prior to writing down those available given is for you to draw or to identify first what type of cycle is being discussed in the problem. Okay? So in this case, as we've read the problem, the working substance of a Carnot cycle, so we know it follows this PV and TS diagram. So why is this essential? So it is essential for you to determine what type of processes is taking place during that points. So from point 1 to 2, it is isothermal, from 2 to 3, isentropic, and the likes. Okay? And as well, in your TS diagram, you need to include wherein the heat addition and heat rejection takes place. Okay? So that it will lessen your lessen the tendency of getting an incorrect answer. Okay? So now, you're identifying a Carnot cycle here. Okay? So the problem states that the working substance of a Carnot cycle is 8-pound mass of air. So after you write or you draw your PV and TS diagram, you can immediately proceed with your given. Okay? So what are the givens that is being handed down to us? So we are given 8-pound mass, which is the mass of the system, mass of the fluid. So that is 8-pound mass of air. So let's write everything that we know about air. So air has a specific gas constant of 53.34 foot-pounds per pound mass Rankine, and then it has a specific heat ratio of 1.4. Okay, so the volume at the beginning of isothermal expansion, so it is stated at the beginning of isothermal expansion. Here is where your PV and TS diagram takes place. Okay, so you need to determine where is the isothermal expansion. Okay, so we know that your Carnot cycle consists of two isothermal and two isentropic relations. So isothermal is from point 1 to 2. So what happened to the volume at this place, okay, or at this state? So the volume increases. So therefore that is an expansion. Therefore it is stated that the beginning of isothermal, so the beginning of isothermal is at point 1. Okay? So therefore we can conclude that 9 feet cube is your V1. Next, and the pressure, so it is stated as well, beginning of isothermal, therefore this is P1, is 9 feet cube. Okay? So next, the ratio of expansion during heat addition. So the ratio of expansion, so let's determine first where is heat addition. Okay, so heat addition based on our TS diagram is in between 1 to 2. So therefore this part, okay, heat addition. Okay, so the ratio of expansion, how are we going to illustrate the ratio of expansion? So we know that heat is added from point 1 to 2, so therefore the expansion or the ratio of expansion that we need to consider is the ratio between the final, which is V2, relative to V sub 1. Because as you can see, from V sub 1 to V sub 2, it expands. Okay? It cannot be 3 and 4 because 3 and 4, as we've mentioned from the previous video, that is compression. Okay? So V2 over V1 said that is 2. And the temperature of the cold body, so it is the sink. So this one, right? So T sub 3 or T3 is 90 degrees Fahrenheit. So if we convert that in terms of Rankine, that is 550 Rankine. Okay? So we are asked to solve for the heat added, heat rejected, V3, P3, V4, P4, MEP. So the MEP is your mean effective pressure, the ratio of expansion during isentropic process, and the overall compression ratio. Okay? So if feel free to pause the video if you want to try it by yourself, and then let's verify our answers with each other. Okay? So, let's start. So, as much as possible, let's try to follow this method. Actually, you can skip one method from another, but that we'll do our best. Okay? So, let's proceed with letter A. Okay? So, as you can see first, we cannot solve for heat added yet. Okay? Because by observation in my given, I have P1, V1, M, and R. I can solve already for my highest temperature, or T sub 1. Okay? By using the equation P1 V1 is equal to MR T sub 1. Okay? So if we solve for T sub 1, that is T sub 1 is equal to P1 V1 over MR. So P1 should be 300, not 9. Okay? So 300 PSIA. Sorry. Okay? So 300, so pounds per inch squared, times V1, that is 9 feet cubed, divided by the mass, which is 8 pound mass, multiplied by R, which is your specific gas constant, which is air, 53.35 foot-pounds per pound mass Rankine. So since this is in inches squared, pounds per inch squared, we need a conversion factor. Okay? So therefore, once we perform our dimensional analysis, so inches squared, so pound force, feet, pound mass. So leaving us with T sub 1. So that is, if we get our calculator, so we have 300 times 9 times 144 divided by 8 times 53.35. So T sub 1, or the highest temperature, is 910.965. 0.965, so that is in Rankine. So actually, we need this information. So since we have T3 and T1, so even though it is not requested here, we can solve for the system's efficiency. Okay? So how are we going to solve for the system's efficiency? So the efficiency in the Carnot cycle, that is 1 minus T3 over T1. So if you want to see the derivation of this one, you can proceed with the previous video wherein we derive this equation. So we have 1 minus T3, that is 550 Rankine, over 910.965 Rankine. So this one will cancel. So we will have the efficiency of, so let's compute for that, 1 minus 550 times 910.965, so that is 0.3962, or approximately 39.62%. Okay, so this is additional information about the system. Okay, so how are we going to solve for the heat rejected? Okay, so before, so the previous video, we have derived that the heat added, letter A. So the heat added is equal to T1, so S2 minus S1, or the change in entropy. Okay, so therefore we can use this one. However, we don't have yet the change in entropy. So therefore we can solve for the change in entropy on point 1 to 2 is equal to Q over T. So Q is not yet given, so we need to derive it using the non-flow equation, PdV from point 1 to point 2 over T. Okay? So if you want to see the derivation of this one, you can look back on our previous video. Okay? So here, the final equation that we will possess here, this is P1 V1 natural logarithm of V2 over V1 divided by T sub 1. And then this one, P1 V1. So we can rewrite this as delta S from 1 to 2 is equal to MR T sub 1 ln V2 over V1 divided by T sub 1. And then T sub 1 will cancel out, leaving us with the change in entropy from 1 to 2 is equal to MR ln V2 over V1. So we have the value of mass, that is 8-pound mass, and R, which is 53.34. So 34 or 35 will do. So foot-pounds per pound mass Rankine ln of, what about V2 over V1? Okay, so we don't have yet the value of volume, but what we have is the value of V2 over V1 already. Since it is given that the value of the expansion, so ratio of expansion during heat addition is 2, so therefore we can immediately substitute that in our equation. So this is 2. Okay, so therefore delta S from 1 to 2 is equal to, so if we evaluate this one, it will be in foot-pounds per Rankine. So therefore we need to divide it by 778. So we have 8 times 53.34 natural logarithm of 2. So we have 295.779, that is in foot-pounds per Rankine. So let's divide it by 778.16. So we have 0.38 BTU per Rankine. Okay, this one is a powerful information for us to solve for QA. So before we proceed here, we know that this one, if you expand this, this is S2 minus S1 is equal to 0.38 BTU. Okay, so if we resume, so BTU per Rankine. So if we take a look back at our TS diagram, so we know that entropy 2 is equal to entropy 3 and entropy 1 is equal to entropy 4. So entropy 2 is equal to entropy 3 and entropy 4 is equal to entropy 1. Okay, so if we are going to solve for this one, so let's substitute S3 here and S4 naman to S1. So we will have, so S2 will become S3 minus S1 will become S4 is equal to 0.38 BTU per Rankine. However, this is improper because this is lower limit minus upper limit, so we need to interchange them. Okay, so once we interchange them, so what will happen to the right side? It will have an opposite sign. So therefore this is S4 minus S3 is equal to negative 0.38 BTU per Rankine. So this is necessary for us in computing for the heat rejected. So that is delta S from 3 to 4 is equal to negative 0.38 BTU per Rankine. Okay? So let's write it properly. This is Rankine. Okay? So now we have delta S. So we can solve for heat added. So heat added is T sub 1. T sub 1 is 910.965 Rankine times, so the change in entropy, that is 0.38 BTU per Rankine. So we can cancel Rankine. We will have QA is equal to, so this one times 910.965. So we have heat added, that is 346.259. 346.259 BT. Okay? So we need to put a box here because this one is a necessary parameter. So this is letter A. Okay? Now, we are asked to solve for heat rejected. So based on our derivation before, heat rejected is equal to T3 multiplied by S4 minus S3. Okay? So wherein S4 minus S3 is here already and T3 is already been given, which is 550. Okay? So we'll substitute that 550 Rankine times S4 minus S3, that is negative 0.38 BTU per Rankine. So if you assess this one, cancel everything, we will have the heat rejected. Take note that the heat rejected should always be lower than your heat added. Okay? So 550 times negative 0.38. So we will have 209. Okay? So negative 209 BTU. Okay? So take note that heat rejected is always negative because it is neglected by our system. So this is letter B. Okay? Next, letter C. So in letter C, we are asked to solve for V3. Okay? But prior to solving V3, I can observe in our given, so we are given the isothermal expansion ratio, which is V2 over V1, and I have already V1. So therefore, I can solve for V2. So V2 over V1 is equal to 2. And our V1 is given by 9 feet cubed. So for solving V2, it is V1 times 2 or 9 times 2. Therefore, our V sub 2 is equal to 18 feet cubed. Okay, so this is a unnecessary parameter, but we need that for solving other parameters as well. Okay, so now I have this one, V2. So the next thing I need to solve is V3. Okay, so let's look at our PV diagram. So we are already here at point 3. Okay, take note that this is not isothermal anymore. This is already isentropic. So therefore, we need an isentropic relation for us to solve V3. Okay, so the easiest way that I can solve for that is using temperature and volume. Okay, so we have T3 over T2 is equal to V2 over V3 raised to K minus 1. So we have values of T3 and T2. Okay, so T3 is 550 and T sub 2 is only equal to your T sub 1 because this is isothermal, so that is 910.65. so 910.965 Rankine is equal to V sub 2, so we have V sub 2 here, that is 18 feet cubed over V sub 3 raised to K. K is 1.4 minus 1. Okay, so Rankine. So actually you can use shift solve here, but we won't do that. So the thing that we need to do here is to evaluate first the left side. Okay, so we will have 550 divided by 910.965, so equals, so 0.603. So 6037.375 equals, so we have 18 feet cube raised to V3 quantity raised to 0.4. Okay, so if we raise both sides by 1 over 0.4, so 0.4 here will cancel out, leaving us with, so let's try to store this. So shift store, I want it to store in variable a. So we have a raised to 1 over 0.4. So that is 0.283. So let's get another significant figure. 2832 is equal to 18 feet cube over v sub 3. So by solving this one manually or algebraically, so v3, that is 18 divided by the answer. So we will have 18 divided by the answer, that is, so we have v sub 3, that is 63.55 feet cube. Okay, so we need to put a box around it. So this is condition number C, or letter C, sorry, it's condition C. Okay, next we are asked to solve for p sub 3. Okay, so as you can see at point 3, this is isentropic relation as well. Okay, so P3 and P2, I can relate them. So how am I going to relate them? So we will use isentropic relation, that is T3. So T3 over T2 is equal to P3 over P2 raised to K minus 1 over K. Okay, so T3, so we have that. So T3 is the lowest temperature. We have 550 over 910.965, so both are in Rankine, is equal to the quantity of P3 over P2. So for P sub 2, actually we don't have P sub 2 yet, so let's try to solve for that. So since here they are so this one P sub 2. Okay, so as you can see, it is an isothermal region. Okay, so we can use combined gas law in an isothermal region, that is P1 V1 is equal to P2 V2. So for solving P2, that is P2 is equal to P1 V1 over P2. So P1, that is let's check. So that is 300 psia. V sub 1, that is 9 feet cube, and V sub 2, 18 feet cube. So by performing dimensional analysis, cancel, P2 is equal to, so we have 300 times 9 divided by 18. So we have 150 psia for P sub 2. Okay, so we can substitute it here. So P sub 2 is 150 psia raised to 1.4 minus 1 over 1.4. So if you evaluate this one, we will get again 0. So if we cancel this one, so we will get 0.60375. So is equal to, if you evaluate this one, this is quantity P sub 3 divided by 150 psia raised to, so this is 1.4 minus 1 divided by 1.4. So this is 0.2857. Okay, so if we raise both sides by 1 over 0.2857, so this one cancel out, leaving us with, so we have 0.60375 raised to 1 over 0.2857. So we will have 0.1709. 0.1709 is equal to P sub 3 times 150 PSI. So for solving P sub 3, let's cross multiply. So P sub 3 is equal to, so multiply this one by 150. So that is 25.64 PSI. Okay, so let's put a box around it, and then this is condition, so P sub 3, that is letter D. Okay, letter D. Next, so let's determine first this one, the ratio of overall expansion during the isentropic process. So let's locate first which one. So we have two isentropic process, 2, 2, 3, and 1, 4. Okay, so which one among them is an expansion? Okay, so 1 and 4, as you can see, so from 4 to 1, this is compression. So definitely not 1 to 4, but 2 and 3. So when we talk about the ratio of expansion, that is V3 over V2. So when we are talking about the overall ratio of compression, so let's start first from the farthest to the least. Okay, so that is, so ratio of, so this one is V3 over V2. So this one is V3 over V sub 1. So actually we have those parameters. So let's try to solve for the ratio of expansion, that is V3 over V2. Okay, so if we want to solve V3 over V2, so V3 we have already obtained that at 65.33, 63.55. Okay, 63.55 feet cube over V sub 2, that is 18. So cancelling the numerator and the denominator, so we will have V3 over V2, that is equal to 63.55 divided by 18, that is 3.53. Okay, so since the units have been cancelled, so we don't need them anymore. So 3.5306, 3.5306. Okay, so V3 over V2, that is letter, okay, so that is letter H. Okay, next, the next one is V3 over V1. So V3 is 63.55 feet cube divided by, so V1, that is 9 feet cube. So let's double check. So V1, yes, 9 feet cube. Okay, so if we want to evaluate this one, that is 63.55 divided by 9, that is 7.061. So V3 over V1, 7.061. Okay, so this is letter I. Sorry, so this one is letter I. Okay, next, so now we have that. So actually we can solve for V4, okay? Because we've derived before in the previous video, we obtained that V4 over V3 is equal to V1 over V2. So if you want to look back on how we derive these values, you can consult for the previous video. So V4 is equal to V3 times V1 over V2, because V4 is a necessary parameter, which is letter E. Okay, so let's do this. So V3, that is 63.55 times V sub 1, that is 9 over 18. So we can simplify this one. V sub 4 is 63.55 times 0.5. Okay, so 63.55 times 0.5 is 31.775 feet cube. So this is letter E. Okay, letter E. So P4, how are we going to solve for P4 now? So let's go back again to your TS curve. Okay, so in P4, so as you can see, 4 and 3, they are isothermal here. Okay, isothermal relation. So therefore, we can use isothermal principles in solving for P4. So that is P3V3 is equal to P4V4. So P4 is equal to P3V3 over V4. So P3 is 25.64 PSIA times V3. So V3 is 63.55, so feet cube, over V4, that is 31.775 feet cube. So feet cube cancel out. So P sub 4 or P4 is equal to, so we have 25.64 times 63.55 divided by 31.775. So we have P4, that is 51.28. So that is in terms of PSIA. So that is 51.28 PSIA. So this is letter F. Yes, this is letter F. Okay, next, after letter F, we are asked to solve for the MEP, or mean effective pressure, that is work over volume displacement. So actually we can solve for the work since we have the efficiency already and heat added. So we will use this equation. Efficiency is work net over QA. So the work net is simply, so work net is equal to QA times E. So heat added, that is 346.259 BTU, 346.259 BTU times the efficiency which we computed earlier, that is 0.3962. 0.3962. So we will have the value of the work net, that is, so of course it is in terms of BTU, so 346.259 times 0.3962. So we have 137.187 BTU. Okay, this is not a box, it should be an underline. Okay, now If you're going to expand this one, the volume displacement should be, as you can see here in our PV diagram, it is the largest displacement of your piston or your system. Okay? So, as you can see, it is from point 3 and point 1. So, therefore, our volume displacement is V3 minus V1 for us to locate the distance traveled by our piston. Okay? So if we expand this one, the mean effective pressure, we can rewrite this one as mean effective pressure is your work net, which is 137.187 BTU over, so V3 is 63.55 minus 9, so that is in feet cube. Okay, so this one is in BTU. We need a conversion factor of 1 BTU is 778.16 foot-pound force. So as you can notice as well, mean effective pressure is a pressure, and majority of the units of our pressure is in terms of PSIA. Therefore, we need a conversion factor here that states in 1 feet cube. Okay, so let's convert na lang that later on once we've performed our dimensional analysis. Oh, actually, we can perform it now. So 144 inches squared per 1 feet squared. Okay, so BTU, feet, so this one will be squared. Feet squared will cancel out, leaving us with pounds per inches squared. So we have the mean effective pressure, that is 137.187 times 778.16 divided by 63.55 minus 9 times 144. So that is equal to 13.59, okay, 13.59, so that is PSIE. So the mean effective pressure is letter G. Okay? So let's take a quick recap. So we've already solved for this one, parameters. Okay? So for letter A, it is 346 BTU. So for that's the heat added. The heat rejection is negative 209 BTU. So V3, or the final volume on isentropic expansion, so that is 63.55. Letter D is, so that is P sub 3 or pressure 3, 25.64 PSIA. Next, for letter E, we have 31.775, and F is 51.28 PSIA. The next one is the MEP, which is 13.59 PSIA, and the ratio V3 over V2, that is 3.5306, and V3 over V1, that is 7.061. So I hope we obtained the same values of those variables. So if not, so you can try to practice again, so repeat the processes again. Just don't forget that once you are dealing with processes of an ideal gas, especially with this one, there are not process of ideal gas, but the gas cycles itself. So especially with this one, wherein you have a lot of conditions that you need to solve, you need to draw your PV and TS diagram. So we can now move on to our next problem. Okay, so for our next problem, the thermal efficiency of a particular engine on an ideal cycle. So you have a keyword here, an ideal cycle. So once you've encountered the keyword ideal cycle, you can easily assume that is a Carnot cycle. So why is it referred to as an ideal cycle? Because we know that the Carnot cycle is the most efficient cycle, or most efficient process of all among the gas cycles. Okay? So it's 30%. So we have an efficiency 30%, or simply 0.3. So we are asked to determine the following. So we are asked to locate the heat source or heat supplied that per 1200 watt hour of work. So we have work, which is 1200 watts hour. Okay, so let's solve for this one first. Okay, so how are we going to measure heat? Okay, or to compute the heat. So as you can see, we are given efficiency, unknown C, unknown of heat added, and work. Work is given. Okay, so we can use efficiency is equal to work net over QA. So as you can see, we can solve for QA by just simply dividing the work net over the efficiency. So the work net, that is 1200 watt hour per 0.3. So QA is equal to 1200 divided by 0.3. That is 4000 watt hour. However, watt hour is not a unit of heat. It should be either BTU or joules. Okay, so if we expand this one, we know that watts is joules per second. Joules per second hour. Okay, so we need to cancel hours and seconds by simply multiplying it to a certain conversion factor. We know in 1 hour how many seconds? That is 3600 seconds. So we can cancel them, leaving us with joules only. So QA is equal to 4000 times 3600. So that is a huge value. So press ENG for scientific notation. That is 14.4 times 10 to the 6, that is megajoules. So that is 14.4 megajoules. Okay, so this is your heat added, or letter A. Next, since we've converted this one, so let's try to convert also this one. So that's 1200 times 3600, that is 4.32 megajoules. So megajoules. Okay, so letter B, the ratio of heat supplied to heat rejected. So let's solve first for the heat rejected. So we have QA and we have the work. So therefore, we can use the equation work net is equal to QA minus the absolute value of QR. Okay, so QR, so we can transpose that. We have work net minus QA is equal to negative QR. Right? So as you can see, the work net, that is 4.32 minus QA, that is 14.4. This should be negative. So as you can see, the heat rejected is 4.32 minus 14.4. So that is negative 10.08 megajoules. So if you obtain the absolute value, the heat rejected is 10.08 megajoules. Okay, so we are asked to obtain the ratio of heat supplied to heat rejected. So that is heat supplied to heat rejected, that is 14.4 megajoules over 10.08 megajoules. Okay, So 14.4 divided by 10.08. So we have 1.428. 428 as the ratio of your QA over QR. Next, we are asked to solve for the ratio of work developed relative to heat rejected. So the work developed is 4.32. So work developed, sorry. So this should be black. So work net over heat rejected. So the work net, that is 4.32 megajoules over heat rejected, that is 10.08 megajoules. So we will have 4.32 divided by 10.08. We have 0.4285. So work net over QR, 0.4285. Okay, so that's simple. Okay, so now we can proceed with our next problem, or the third and last problem for Carnot cycle. Okay, so for our last problem, a Carnot engine operating between 900 degrees Fahrenheit and 90 degrees Fahrenheit. So as you can see, it is already provided T1, so the highest temperature, and T3, which is the lowest temperature. So we have 900 plus 460, so that is 1360. So this is in Rankine, and 90 that is 550 Rankine. So it produces a work that is 40,000 foot-pounds. So for formalities, let's convert this one in terms of BTU. So that is 40,000 divided by 778.16, that is 51.403 BTU. So we just convert this one. So in 1 BTU there is 778.16 foot-pound force. Okay, so we are asked to solve for the heat supply. Okay, actually the first thing that we can solve here is the thermal efficiency, since we are already given T1 and T3. So the efficiency is 1 minus T3 over T1, or 1 minus 550 over 1360. Okay, so the efficiency is equal to 1 minus 550 over 1360, so that is 0.5955, or approximately 59.55% efficient. Okay, so now we have the work and we have the efficiency. We can use efficiency is equal to work over QA. So QA, or the heat supplied, is 51.403 BTU divided by the efficiency, which is 0.5955. So QA is 51.403 divided by the answer, that is 86.306. 306, so that is in BTU. Okay, so this one is letter A and this one is letter C. So how are we going to measure the entropy during heat rejection? So in our TS diagram, heat rejection is the lower limit. So that is 0.3, 0.4. So this is your TS diagram. So this one, this is T3 and DS. Okay. So the change in entropy from points 3 to 4 is equal to Q3 over T3. So Q3 corresponds to your heat rejected. So therefore, we need to solve first for our heat rejected. So the heat rejected, so it should be negative, right? So the entropy here should be negative. So as you can see here, we have the work net is equal to QA minus QR. So the work net is given by 51.403. So that is in BTU is equal to QA, that is 86.306 BTU. Okay, so minus QR. So here we need to obtain the absolute value of this one. So QR is equal to 51.403 minus 86.306. So that is negative 34.903. That is in BTU. Take note that heat rejected is always negative. Okay? So that is your heat rejected. No, should not be boxed. Should be underlined. Okay? This is your heat rejected. So therefore, we can substitute it here. It is negative 34.903 BTU divided by T sub 3. So T sub 3, that is 550 Rankine. So therefore, the change in entropy at points 3 to 4, that is equal to so 0.063 0.06346. So negative 0.06346 BTU per Rankine. Okay, so this is letter B. So I hope we obtain the same values. So in the next video, so we will try to cover naman auto cycle. Okay, so I hope you've learned something. So stay safe and take care to everyone.